What's going on? So today we're going to go on to the next section involving limits. So this one's going to be a little bit more algebraic as we start to teach you some of the tricks that you can use to kind of help yourself evaluate a limit when sometimes it just doesn't work out when you use direct substitution. Okay, so we're going to go ahead and start. So the first one we're going to be focusing on is called the dividing out technique. So really quickly, if we did use direct substitution here, I would get -3 squared plus -3 minus 6 over -3 plus 3. Alright, so let's see what we get as a value. So in the numerator, this is going to be 9 minus 3 minus 6. And then we're going to have 0 in the denominator. The numerator is going to end up being 0 as well. Alright, now whenever we get this ratio of 0 over 0, we actually call that the indeterminate form. Right, so we don't know exactly what this value is equal to because it doesn't file. There is no rule for it. 0 divided by 0 is just not something that we know. So we say it's indeterminate in terms of us evaluating the limit. All right, so we just don't know what's happening. Now, if we did this one instead of using direct substitution, if we actually made a table, we would actually get a pretty good result here. All right, so let's say I created a table and we're finding the limit as it approaches -3. Okay, so I need to go -3.001. And we'll go a few above, a few below, and kind of see what value it's approaching. Okay, all right, so really quickly, we're going to have parentheses in the numerator. I have -3.01. Alright, what are we doing here? To the second power plus -3.01 minus 6. In the denominator, I'm going to have -3.01 plus 3. Alright, so we have -5.01. If I add another 0 in there as we get closer to the -3, I'm going to get -5.001. Okay, on the other side, approaching it from the right hand side, we're going to go -2.999, 2.999, 2.999. So I get -4.999. Okay, and if we remove one of these 9s here, I get -4.9. Okay, so based on the table, okay, as we see here, we can kind of tell that the limit of the function backspace here. The limit of the function that we have as x approaches -3 is going to be equal to -5. Okay, so again, here's a case where direct substitution just didn't work out. It gave us indeterminate form, but using the table method actually gave us the limit. Now, we don't always want to use the table because it just takes kind of long, you know, when we do it often. So dividing out technique is what I'm going to show you. We'll do the same problem using dividing out technique. So what I want you to realize here is that this function, okay, is actually a rational function, and we could probably simplify that. Okay, so that's what we're going to do in the next slide, algebraically, and let's see how the limit works then. Okay, All right, so here I have this function. So what I can do with the function is I can factor the numerator. So I'm going to get x plus 3, x minus 2 over x plus 3. Okay? All right, so what's going to happen here is that they have a common factor of the x plus 3. So that's going to simplify for us. So all we're going to have left here is x minus 2. Okay? So algebraically, the function simplified to x minus 2. Okay, now, if we find the limit of this x minus 2 because it's equivalent to the one before, it would give us the limit of the function. So here, using direct substitution, I get negative 3 minus 2, which is negative 5, and we said that that was the limit from the previous slide. Okay, so this is the value that we found. It worked wonderfully when we simplified it. Okay, direct substitution became very easy at that point because you're just substituting to a nice linear function. And then there you go, there's your graph. Okay, now I do want to explain the graph a little bit of this function compared to this function. Okay, so if we look at the two graphs, they're going to look very similar. Okay, because the function simplifies to this x minus 2 here, both of these graphs are going to kind of look like the line here. So let's say that that's minus 2. Okay, okay, both of these functions are going to somewhat look identical. All right, so the behavior for each of these functions is going to be the same. Now, the only thing that's different is that this is x minus 2, and this was the function that was given in the problem. Okay, notice that here we have a closed circle of x minus 2 because it exists at 0. Or it exists at negative 3, should I say. Okay, and at negative 3 we have a value over here. Right, so basically what's going to happen down here is we actually have a hole at negative 3. Okay, and since there's a hole at that value, that's why when we use direct substitution here, we get indeterminate. Okay, but when we simplify, we get an actual value when we use this function as a reference instead. Remember, the limit does not matter if it exists at that point in the function. What matters is that the behavior from both sides of the graph are equaling the are approaching the same value. Okay, so let's look at another one using the dividing out technique. Okay, so find the limit. All right, so what you're going to do is you're going to factor the denominator. The numerator is going to be x minus 1. Okay, now the denominator we can factor by grouping, so I can have that as x squared times x minus 1 plus 1 times x minus 1. All right, so this is going to equal x minus 1 over x minus 1 x squared plus 1. All right, so algebraically, what is going to simplify? We're going to simplify here. So I'm going to get 1 over x squared plus 1. Okay, so now algebraically, okay, I can plug in the 1 into this function, okay, and I'm going to get the same limit as I would here. Okay, so I'm going to do the limit as x approaches 1 of 1 over 1 squared plus 1. That's going to give me 1 over 1 plus 1, which is 1/2. Okay, so the limit as x approaches 1 is going to be equal to 1/2 of the original function. Now, if we plugged in 1 into the original function, notice that you're going to get 0 over 0, which is going to be the indeterminate form. You get 1 minus 1, which is 0. You get 1 minus 1 plus 1 minus 1, which is also 0. So you're going to get indeterminate. Right? So when it's indeterminate, you have to see if you can use any algebraic technique to kind of help you simplify it. In this case, we were able to use the dividing out technique, which kind of helped us out simplifying here. So the limit as x approached 1 was equal to 1/2. Okay, the rationalizing technique. Okay, so really quickly, if we plugged in 0, notice we will get 0 plus 1 minus 1 over 0. We're going to get 0 over 0. We know that that's going to be indeterminate. Because that's indeterminate, there is no limit as of right now, for this function, we have to see if we can use an algebraic technique to kind of help us out, okay? Now, it's called rationalizing technique, but if you guys notice, the radicals, from what we know in the past, when we rationalize a fraction, we usually rationalize the denominator so that the denominator is no longer rational and the numerator has all, the denominator is no longer radical, and the denominator now has a rational number. Okay, but instead of rationalizing the denominator like we're used to, we're actually going to be rationalizing the numerator. We're kind of just undoing that simplification in a sense. So what's going to happen is our radicals are going to be on the denominator, but that's actually going to be very helpful for us when we actually evaluate the limit. All right, so let's take a look at it. Okay, so you're going to start with this expression. We're going to multiply by the conjugate. So the conjugate is going to be radical x plus 1, but instead of minus, we're going to go with plus 1. Okay, and then same thing in the denominator. It's going to be radical x plus 1 plus 1. Okay, so when we rationalize in the numerator, I'm going to have the product of the first two in the first two position of the binomials, so that's going to be x plus 1. We're going to have plus radical x plus 1 minus radical x plus 1, so those are going to cancel out, and then I'm just going to have minus 1 in the numerator. In the denominator, I'm going to have x times the square root of x plus 1 plus x. Okay, so now this is the function that we kind of simplify to. So now we're going to evaluate the limit, okay, as x approaches this value of x plus 1 minus 1 over x square root of x plus 1 plus x. All right, so again, the limit's going to work the same way because since it's an equivalent function, the behavior is going to act the same, okay? Because all we did here was multiply by 1. So the value of the function stays the same, so the graph, it's going to look the same. It's just we wrote it in a different form, okay? So if we evaluate the limit of what we simplified to here, we're still going to get the same limit as the original function. It's just when we first plugged it in using direct substitution, we got indeterminate form. Okay, so here we're going to get 0 plus 1 minus 1 over 0 times the square root of 0 plus 1 plus 0. Okay. Notice that we're still getting 0 over 0. Okay. Now, the one thing we have to do when we rationalize is we have to make sure everything is completely simplified, right? Okay. Notice that here we kind of have these common factors of x. So I can kind of factor that out some more and kind of help me simplify this the best we can, okay? So let's continue on factoring because as we said, sometimes it's going to work right away when you rationalize, but in this case it didn't. So we have to try to find another method of simplifying once we got to this form. So the other way to do it, all right, so let's get some space here. I can erase some of this up here because we already knew how to do that. So now what we have, if I simplify it, is we're going to have x because plus 1 minus 1 is going to cancel. Okay, and then in the denominator I have, if I factor it, x times square root of x plus 1 plus 1. What's going to happen with these two x values? The two x values are going to simplify, so I get 1 over the square root of x plus 1 plus 1. Now if I plugged in 0 for the limit, I'm going to get 1 over square root of 0 plus 1 plus 1. So I get 1 over 1 plus 1, which is 1/2. All right, so this limit is equal to 1/2. Okay, so again, algebraically, we have to simplify the function as best as we can. They're rational functions, so you just have to find that common factor that's going to help you simplify. If you have a radical in the numerator, it's important to rationalize that radical and move it to the denominator so we can kind of work with that. All right, so let's look at this one here. We have the limit as x approaches 0 of the square root of 2x plus 1 minus 1 over x. So if I plug in the value of 0, I'm going to get 0 plus 1 minus 1 over 0, which is going to give me 0 over 0. That's indeterminate. So we're going to rationalize the numerator. So we're going to multiply by the square root of 2x plus 1 plus 1, square root of 2x plus 1 plus 1. All right, so when we multiply this out, the numerator is going to be 2x plus 1 minus 1. The denominator is going to be x times square root of 2x plus 1 plus 1. In the numerator, I'm going to have 2x over x times this radical 2x plus 1 plus 1. Algebraically, what's going to simplify for us? These x's are going to simplify. So what we're going to have here is we're going to have 2 over the square root of 2x plus 1 plus 1. All right, so now what we want to do is we actually want to find the limit of this as x approaches 0. Okay, and that's going to be 2 over the square root of 2 times 0 is 0, so that's going to be square root of 1 plus 1. So we're going to get 2 over 2, which is equal to 1. So the limit of this function as x approaches 0 is equal to 1. All right, so again, the two methods that we have here are dividing out and rationalizing. So when we're rationalizing, again, multiply by the conjugate of the radical expression that's provided. The radical should move to the denominator. What's going to happen is you are going to have a case where you're going to have to simplify a variable. You simplify the variable, and then you algebraically use direct substitution. Okay, same thing with the other method. The other method was the dividing out technique. Okay, plug it in originally. If it's indeterminate, simplify the fraction algebraically, plug in the limit again, and it should work nicely. Okay, so again, we're just using direct substitution, but the problems are a little bit more advanced because you have to apply some form of algebra 2 to kind of help you guys simplify the process. All right, so hopefully this helps you guys. Thanks for watching.